recent achievements in design of new energy materials for sustainable and clean energy supply. So now let me begin by talking about the motivation of our research project. Nowadays, global warming is one of the most serious global challenges. According to the report of the Intergovernmental Panel on Climate Change, the global temperatures in 2020 have risen by 2.1 degrees C compared with 2000, and they will rise by 3.3 degrees C in 2030. So global warming and climate change are associated with the vast amounts of greenhouse gas emissions by extensive combustion of fossil fuels. Such excessive consumption of fossil fuels also causes another challenge of energy shortage. According to the World Energy Outlook of the International Energy Agency, the worldwide demands of oil, coal, and natural gas are expected to rise to 53, 50, and 38 gigatons in 2030. However, fossil fuels have limited reservoirs, and the production of fossil fuels hit the highest peaks already in 2020, and then decreased continuously. To mitigate the catastrophic effect of global warming and ensure the sustainable energy supply, we must switch over to the renewable and clean energy sources, including solar energy, hydro, wind, tidal power, and geothermal energy. In fact, majority of national and global energy policies include a framework strategy towards greater sustainability and energy security. So what are the subjects of our research work? The first is solar cell. So solar cell is an effective device for harvesting solar energy by photovoltaic effect. Recently, perovskite solar cells have emerged as a third generation of solar cell with the initial power conversion efficiency of 3.8% and extremely fast rise in efficiency compared with other conventional solar cell, like 25.5% within decade. However, for commercialization of PSCs, we should address the fundamental problems such as like device and material instability to the external factors such as moisture and heat, and scalability for large area modules. Another subject is photocatalyst. So solar water splitting using sunlight is also an effective way for solar to chemical energy conversion, producing hydrogen gas as clean fuel. So in this direction, the research focus is being paid to the design of a new photocatalyst for facilitating the hydrogen evolution reaction. So the desirable photocatalyst should have unique material properties, including broad and strong light absorption, efficient charge separation, and long operational stability, and also the appropriate redox ability for hydrogen evolution. In promoting such natural energy policy, the efficient electrochemical energy storage techniques should be developed for the grid-scale energy storage system and electric or hybrid electric vehicles. Due to the natural abundance and low cost of sodium resources, sodium-ion batteries have attracted great interest in recent years as a promising alternative to lithium-ion batteries. But the larger ionic radius of sodium-ion cause great difficulty in finding suitable electrode materials for commercially viable SIBs with high energy density and long cycle life. So in this lecture, I'd like to talk about research work for perovskites and photocatalyst and sodium-ion battery electrode materials based on first principles modeling and simulations. Now, let me talk about the working principle of PSC, which is different from the silicon solar cell. You can see that the perovskite solar cell consists of several layers like perovskite layer, hole transport layer, and electron transport layer, which are placed on glass with a thickness of about 2 micrometer. So that is, it is very simple and flexible solar cells. Here the perovskite layer plays the key role absorbing photons coming from sunlight and generating the charge carrier of electron and hole. And this photo-generated electron and hole extons are separated by the interface bias and transferred to ETL and HTL, and then to the anode of fluorine of the tin oxide and the counter electrode of AUO and AZ respectively. So Perovskite is one of the most important crystalline structures in materials science, and its chemical formula is ABX3 with a great diversity of composition. So here A is the monovalent cation, like organic or inorganic iron, and B is the divalent metal cation, and X is the halide anion. So the most widely studied halide perovskites is methylammonium lead iodide, 3-iodide, MAPI, having a proper band gap of 1.5 electron volt for absorbing visible light. So when contact with titanium dioxide, ETL, and organic molecular HTL, the photo-generated electron and hole can be transferred to them due to the appropriate band gap alignment. To improve efficiency and stability and resolve the toxicity from lead, we can tune composition at each side with band gap engineering by applying the GW and HSE06 method. So, the frequency-dependent dielectric constant and thus photoabsorption coefficients are the primary properties of photoabsorber and can be calculated by solving the Bethe-Sulfate equation. So this method gave the results agreed well with the experiment for MAPI. For MAPI solid solution mixed with chloride, we calculate the microscopic dielectric constants. Here we found that the static dielectric constant are related with the rotation of a molecular cation, and while the high frequency or optical dielectric constant is related to the vibrational polar phonons of the lattice. In relation with this, the onset of photoabsorption and the first peak shift to higher photon anodes, like exact the short wavelength light with increasing the mixing content. Defects in semiconductor displays the operating processes like the generation and transport of charge carriers and ion diffusion. So we calculate the formation energies of typical vacancy defects with various charge states in MAPI and its hydros phases and at different thermodynamic conditions. So we determine the dominant defects that has the lowest formation energy and the thermodynamic transition levels, and providing an evidence of degradation of PSCs under humid condition. So we also calculate the vacancy-mediated iodine degradation in MAPI and its water intercalated and monohydrate phases. So we found that the insertion of water into MAPI reduces the activation errors for ion migrations, indicating the easy decomposition of MAPI under humid condition. So whether or not the perovskites are unstable with respect to chemical decomposition is also an important issue. So we found that for MAPI, all the possible phases are unstable for chemical decomposition, and substituting bromine or chlorine for iodine changes the formation energy from exothermic to endothermic, giving the evidence of interface for evidence of performance enhancements. So systematic study on mixing iodine with bromine or chlorine in MAPI, so can provide the turning point for the chemical contents where the chemical decomposition changes from exothermic to endothermic. So we also study the temperature and pressure synergistically on chemical stability of cesium halide perovskites by plotting the three-dimensional phase diagram. And so we find that the cubic CS PBI crystal is stable within the area of a photocircle with a boundary points of 560 Kelvin and 1.3 gigapascal. And the area of chemical stability gradually increased with the bromine content increases. So we then studied the thermal property of halide perovskites, which is also important for PV performance and thermoelectric performance. So we found that the germanium-based cesium halide perovskites exhibit ultra-low thermal conductivity and high carrier mobility, which provides them as potential thermoelectrics. So we found that, so we performed the first principles lattice dynamics combined with temperature-induced unharmonic phonon renormalization revealing that these perovskites have high thermal power factors over being comparable or superior with those of germanium tellurium alloy. And they have also the high thermoelectric figure of merit ZT over 1 by N-type doping, being attributed to strong lattice on harmonicity and the flat dispersible electronic bands with high degeneracy. So then, due to the presence of several interfaces, significant research efforts have been devoted to the interface engineering to achieve a substantial breakthrough in PV performance through the surface stress passivation, compositional tuning, and band alignment alteration. So we have shown that the interface formation of MAP interfaces with Lewis-based molecules and graphene, the binding strength with S-donors, thiocarbamide, and thioacetoamide is higher than with O-donor, dimethyl sulfoxide, while the interface dipole and work function reduction tends to increase from S-donors to O-donor. So we also devised atomistic modeling of superlattice composed of MAPI and CSPBI3 crystal and estimate the formation energies of interfacial vacancy defects and revealing the shallow transient states for most of the defects and higher activation values for vacancy-mediated iodide migration across the interface, indicating the evidence of performance enhancements by the interface formation. So that's all for perovskite, and now I'm going to talk about the design of a photocatalyst for water splitting and hydrogen production. So we studied molybdenum disulfide heterostructures with graphene variants such as graphene and graphene oxide and their boron and nitrogen doped variants. In these complexes, MOS monolayer act as photoabsorber and catalyst for oxygen revolution reaction, while the graphene variants layer acts as electron acceptor and catalyst for hydrogen evolution reaction. So we verified that upon the formation of the interfaces, some amount of electronic charge transferred from MOS layer and the GV side, creating interface dipole and work function reduction. Upon the photo-generated electrons transferred to GV side, so we have studied the hydrogen absorption on GV side of these heterostructures and calculated the Gibbs free energies for hydrogen absorption. So we found that boron and nitrogen doping into graphene result in degrees of adsorption energies, and nitrogen doping is more favorable for hydrogen evolution reaction. We also find that potassium iodide perovskite solid solution also can be a candidate for photocatalysts. So then I'm going to talk about solid sodium-ion batteries for large-scale energy storage system, because sodium is the first most abundant element on Earth and has seemingly unlimited distribution on Earth. So the working principle of SIBs is locking chair mechanism, such that sodium cation shatters between cathode and anode materials during charge and discharge process. So the high performance electrode materials are required to have first high energy density, and second high rate capability, and third long-term cycling stability. So we have done several research work for discovering electrode materials of sodium-ion batteries. So for cathode materials based on polyanionic sulfide, so aldehyde, we find the mechanism for ionic diffusion and electron conduction. So we suggested the inserted sodium atom to diffuse along the two-dimensional pathway with the preceding movement of the host sodium atom, and polaron formation and hopping for mechanism for electron conduction in these materials. And we propose sodium manganese materials also can be potential cathode materials. So our calculations reveal that these materials have low expansion, volume expansion rates below 5%, and electrode voltage range increases from manganese to nickel, So indicating that high energy density can be realized by intermixing French metals because of higher capacity, specific capacity, and higher electrode voltage. So then we also devised anode materials of SIBs. So here the graphite is the most widely used anode materials for commercial LIBs, but due to the larger ionic radius, the sodium hardly intercalates into graphite, and thus the graphite itself cannot be used for SIBs. Here we demonstrate that with organic molecules such as alkylamine and degradation, the sodium can intercalate into graphite, and thus forming one-stage ternary graphite intercalation compound. So we revealed that alkali cation with large ionic radius diffuse more smoothly in graphite, and the solvate ion can diffuse relatively fast, and the electron conductance can be enhanced after core intercalation. So we proposed to use the 2D hybrid composite of tin disulfide with graphene or graphene oxide films as advanced anode materials of SIBs. So we found that the graphene and graphene oxide film can effectively support not only the stable formation of a heterointerface with tin dioxide. So we find that these materials also can be advanced anode materials of SIBs. So then there are several polymorphs of sodium titanate that can intercalate to sodium cation reversibly, and thus that they can be also anode materials. So we studied electrochemical properties for 3 kinds of sodium titanate with unique structures of one-dimensional tunnel and step-layered structure, which are very beneficial for sodium intercalation and migration. So in summary, we have studied advanced materials for solar harvesting and electrochemical energy storage by using the molecular modeling and simulation techniques. So for solar harvesting device of perovskite solar cell, we have focused on photo-absorbing halide perovskites, such as cesium halide perovskites or methylammonium lead iodide, sulphides, and double perovskites. So we will continue on hybrid halide perovskites for increasing the power conversion efficiency of 30% and stability compared with silicon solar cells. We also studied the photocatalyst for water splitting and hydrogen production by using the molybdenum disulfide with graphene variants, and also the halide perovskites demonstrating a vital role of interfacial quantities of hydrogen evolution reaction. So finally, for the grid-scale electrochemical energy storage systems that can be used in intermittent renewable energy sources and electric vehicles, we investigate the cathode and anode materials of SIBs. They are like sodium transition metal oxide and ternary graphite intercalation compounds. So we go a long way in adopting SIBs for commercial purposes and greatly enhance their feasibility. So I thank my group members in Faculty of Materials Science of Kim Il-sung University and foreign partners, Professor Aaron Rice in Imperial College London, UK, and Professor Stefan Cottenier in Ghent University, Belgium, and Professor Suzhou Li in Nanyang Technological University in Singapore. Thank you for your attention.